speakers.
All right, thank you very much. We heard now impressive how it works for MCDI. I'd like to show you a little bit what we do on the FCDI story. We also heard today what we're going to do there. We are also in the field in FCDI since 2014, 2015, when we published the first paper in Aachen. If you don't know that, so when there is the border between Germany, the Netherlands, and Belgium, that's where we are, halfway between Paris and Berlin. All right, so let's talk about scale up and pilot plant implementation of this flow electrode and what we did there. Our focus is more on the ions and not so much on the water, and that's why I usually put this. So whenever we have a chemical plant, we need raw materials, usually salt. We get a wastewater. Usually we're looking here that we get good water to the environment back. But what we like to do, and that's what we envision, is we want to recover a lot of those valuable ions and bring them back into the chemical process. How we do that with flow electrode capacitive deionization. I think I do not need to explain that. The only thing I'd like to explain here is that we use this configuration here, which we in Aachen then call a single module. So we have two cation exchange membrane, anion exchange membrane in the center, and on the outside there is the flow electron being recycled. When we took this scheme and went for a big scale up, we needed to check what are the materials. And the first material we had issues with were this graphite plates. We also had this talk before, and the question, how can we replace them? So I'd like to focus on that one first. You know that there is also a lot of research work going on how this percolation network works, how charge is there transported. And what we did a couple of years back was inventing the idea that we can have a cation exchange membrane and directly laminate a conductive fiber network on top of that. And by that, we get something which I call a single point of contact. So ions would move through the cation exchange membrane and directly get charged at the surface. And this also gives us the freedom that at the end, that for a flowing, for pathing or whatever, or for a meandering structure, we have now the freedom that we do not need a non-conductive housing, not conductive flow field, whatever you would like it to have it. How does this membrane electrodes now look like? You've seen some of those pictures before. I also have seen them today. So this is actually how they are when we produce them. That's when they are swollen. You can also see that this fiber fabric then works, as I call it, a functional reinforcement. So we have two things. We have the reinforcement of the membrane itself due to by its swelling. We have a good detachment. It also saves the abrasion, secures the membrane towards the forces of the flow electrode. And it also gives this nice pattern on the water side, which also then may involve some mixing at the surface of our concentrate or dilute channel, if you wish. Now we take those membranes now at the end, and then we want to go into scale up. So usually we have the small cells, 40 square centimeters membrane area, as most of us are using in this field. And now we want to go big. And if I now tell you big, now I give this number here. We have now 25 times 25 square centimeters. And here we usually have some 3.2 square meter of membrane area in one of those modules. Now let's look a little bit deeper. I'd like to share knowledge what we had on the development here with you. The first thing we looked into is how many cell pairs do we do like. There is a lot of comparable things between FCDI and electrodialysis. So that was one of the first questions. Usually we have one dilute, one concentrate channel. And the question was, can we maybe use the potential between those flow electrodes more efficiently? We usually apply here 1.2 volts by, for example, introduce more of those channels here, maybe a second one, maybe a third one. We did some lab experiments on that with a, sorry, that was the wrong button. A rather high salt solution. That's also what we are aiming for, specifically in Aachen for the high salt solutions. And you can see here the average salt transfer rate. And we can see that with the number of cell pairs, and for 1 or 2 cell pairs, that's pretty similar. Yet for the third cell pair, it drops a lot. And that made us to say, okay, we saw this in several experiments. Well, let's go for 2 cell pairs, and that's designs, so to say. So next thing, now we know when we do 2 cell pairs between 2 flow electrodes. Next question is, how do we stack this? Because we don't want to have only 1 unit, we want to have a lot of them. So we need to think about stacking units. And there what we actually did is we reused the flow electrode a second time, so no bipolar plate. We've also seen this and heard about that. So we have minus and plus, and then we would stack here now the second unit, and this devolves now into the large cell, which you have also seen, not to the number of 20 stacking units within one of those cells. At the end, the module, here's a rendering. This basically looks like that. So you can see that we also apply end plates. We have now our non-conductive flow fields here, which we could either do by injection molding or by 3D printing. That's both possible ways we're applying. Then we have the membrane electrode assemblies here applied for anode and cathode. And in the center, there is the stack of anion exchange membranes and also the spacers for the water field, right? Dimensions you can also see there. Then we were really lucky also to get some funding for a pilot plant. That's what we call a pilot plant. You can see now the module down here. I framed it also with FCDI. So that's everything what's around that. And now it makes my heart really lucky that a lot of people in the past questioned me, what's now the difference between FCDI and electrodialysis? So in this pilot plant, that's what you can also see in the upper part. We could take the same water, the same plant, everything same, yet down there we have an FCDI module, up there we have electrodialysis modules, and see one-to-one what's the difference. Let's talk about the operation, how it works. Defined by the project we're working in. We defined certain conditions for the FCDI part. That's where I'm focusing on. We circulated 15 weight% activated carbon slurry. We are also feeding now as a MOX solution sodium chloride in here. Sodium chloride is then also recycled in a batch mode. And then actually what our plant does by measuring the conductivity here is that we have two containers here which do have actually different volumes. And what happens is we start at a certain conductivity. The conductivity is reduced by the process. If the plant checks that we reach a certain value, it takes a new batch of water and starts the process again. And actually in parallel, the same also works for the concentrate. Defined by limit, it just gives batches through the plant. How does this look like now in batch operation? We can see now that the conductivity drops for the dilute over a certain period of time, and we can also repeat that. So that's actually data we did in the autumn of last year. You can see that if we would recalculate it for a continuous flow rate, we are now up to 36 liters per hour, and the batch is about 8 hours. When we now look also in the concentrate data, it looks like that. Just forgot to mention that here in dilute, we went from 12.5 to 2 grams per liter. In the concentrate, it's a little difference, again, defined by the project environment. Here we go from 32 grams per liter to 74 grams per liter. You see that by the different concentration ranges, also the batch times differ. Flow rate here is a little lower. And what I'd also like to highlight is that you can see all these kings here usually in the concentrate concentrate conductivity curves, and that's actually every time when the batch of the dilute tank is actually changed. That's what you see in the concentrate conductivities, but you do not see this in the dilute concentrate channels. So that's the data we did in last autumn, and then the question at the end was to ask, is this now any good? How does this compare to electrodialysis? What can we learn from that? And there I'd like to take two main results. The first result is what we learned through the scale-up. Well, I showed you already the data of the cell pairs. Now I'd like to go for the stacking units. You can see that we also did the stacking in the small lab scale, and you can see for 1 and 2 is again good. But with the third stacking unit, our sand transport rate per area is actually dropping. And now if I give you also the number for a big module, it's getting even worse. And I also like to have numbers maybe from the industry. If you have also can share this at once, maybe encourage you to share all this data, because we think in Aachen that we can develop a lot and tune a lot on the electrodes and on the surfaces, on a methodology at the end. But when you build a big module, it comes all down to fluid mechanics, to very simple engineering costs, how do you distribute the flow in your module, and then you get such issues here. But that's just one take-home message. We still want to compare this to electrodialysis because they do have the same problem in a plate informed module. So we made these quartet cards, these trump cards, let's say, and just put on the main figures. That's maybe also what you do when you go for a business. Say we have some flow rates, we need some energy in our case, which is 11 kilowatt hours per cubic meter. And then let's compare what we have for the electrodialysis stack. Same membrane surfaces applied here. You can see that we have 4 times the volume flow rate in the electrodialysis case, yet we have 7 times the energy consumption. So we can prove here that electrodialysis in this certain case needs more energy. So at the end, it all comes down the question between CAPEX and OPEX. Also, we just heard about that in a couple of talks before. The question is, do you want to apply a lot of energy or do you want to buy a lot of plant, so to say, and that's the field we are living in when we are just looking at concentrating and not playing the game, maybe of selectivity, which we can do at the end. With that, I also like to summarize what we are generally doing in Aachen in FCDI. You've seen that we worked a lot on charge transport, also on impedance spectroscopy, also on the activated carbon motor slurry. You've heard the talk of Nelson Freire. We are also working on the salt metathesis work, where we're targeting especially lithium recycling. You've heard the talk of Kerstin Bröckelmann. And I'm pretty happy that we now can do those 2 pilot plants here and check how this is going. One of those pilot plants is now working since the beginning of the year, and I'm pretty happy to share the data when we meet the next time. As our customers really like our technology, we're also on the way to spin this salt technology out. The company is called Amovion. Please stay tuned. I think there's a lot to come. You can also get in contact with us so we can learn from each other and maybe do not do mistakes again around the world. With that, I'd like to thank the FCDI team in Aachen. I'd like to thank all the sponsors and project partners which are with us on our journey. And especially I'd like to thank you for your attention. I'm looking forward to your questions.
Any question or comment?
So when you made a comparison between your system and ED, can you tell us more about the catalyst that you use for the ED cell?
So what we have here is sodium sulfate as a electron rinse solution, and the catalyst on the surface I cannot tell you because that's a commercial cell we bought off the shelf. Mm-hmm. So I would need to ask. I think that might be a titanium MMO or titanium iridium coated electrode at the surface, but I actually don't know. We bought that from an ED company from Germany and said we'd like to compare it with what you can buy actually off the shelf.
Okay.
Is there any questions?
Very interesting talk. The connections that I am seeing there in your cell, it seems like you are applying voltage in each one of the cell. Is that right? So you don't do I always get confused with series or parallel, but our understanding is when you apply from the sides, like people from Scientech, probably it's easy to make the connections and it's easy to operate. I don't know if you can comment on that. What did you select, one or the other?
Yeah, so that's actually also the comment we had on the thickness of the copper wires. Mm-hmm. I would say at this stage the copper wires are at a certain size where we hope to still can handle it. Mm-hmm. And the question is, do you want to have a bipolar plate or not? And if you want to have a bipolar plate, how do you produce it? What do you do in the geometry? And we do not have only one phase like in CDI, only water around the electrodes. We now need to handle 4 different channels. That's what we actually need to do here. And that's why we said, okay, we skip the bipolar electrode, make it easier because we can then use induction molding, 3D printing and things like that. And for now, just do this, what you call an electrical parallel setup. So a lot of current and less voltage.
Yeah. Thank you.
Christian, a very, very interesting talk. Your system is rather different to ours, where we pull the salt ions into the flowing electrodes, whereas you don't do that. So you maintain constant ion composition in your flow electrodes, whereas in our case, they're changing, which is perhaps a little problematic, but interesting difference between the two systems.
Yeah, that's true, and it also has some beneficial part, and also because in the past there was a lot of configurations. We were all tested. You did the work how to scale up. There is the honeycomb structure, which was also done before. How we can scale up this. We do this cycle because we believe when we can keep the concentration in the flow electrode, the salt concentration in the flow electrode at a certain level, we can also control a little bit more what happens on the osmotic pressure, especially when we drive this really high concentration differences. I call this high concentration differences. And also what happens in the phase of when you think about selectivity. From a chemical engineer's perspective, it's always best to work at steady state.
And Christian, please look at this chat.
Oh yeah, we have a question. Maybe I can read here. Please recheck the energy consumption for ED. It shouldn't be this high. Yeah, we can recheck that. Maybe you have a better system, but what we actually did is so this is a difference as I mentioned before for going up to 40 grams per liter. We actually put a power meter on the plug of the pilot plant and measure it there, so it's not calculated or something. I think when you do low concentrations, then it's low energy. If you do high concentrations, then you need to spend more.
Thank you. Give a big hand for these outstanding speakers. Now we are final speakers. He's Dr. Chen Xiangfeng. He is working with the Professor Chang Hu.